Just a first small introduction. Yeah, I'm Pim van der Haa. I work for Diana at the engineering department. And on a daily basis, yeah, we cope with engineering projects and also with engineering problems such as safety. And in any calculation we do, we should be sure that we make a safe analysis. So yeah, and this is the contents we're going to how I'm going to do today. First, a small introduction on the safety formats which are already there for nonlinear finite element analysis. Then I will be giving a live demo on strength reduction for total strain concrete. I will give a little bit info about the background theory, and I will discuss the results. And then there's time for some questions and remarks. In the FIP model code, there are 3 safety formats which you are allowed to use for nonlinear analysis. That is the probabilistic method, the global resistance method, and the partial factor method. Yeah, the probabilistic method is the most detailed method. In that method, you're going to do a variation of all the input parameters, as well as a variation over your structure element. And yeah, by that variations, you should be able to figure out what is your reliability of your structure and of your analysis as well. So which safety factors should I use? Then you have the global resistance method. There are 2 methods in that one. Basically, you're going to do a finite element analysis using a mean properties, so material properties. And then you're going to reduce that by a material factor. In terms, yeah, when you're using the ECOV method, that's the second one. That's also probably one which is used most. Then you're going to do 2 analyses. One is with the mean values, and one is with the characteristic values. And based on what is the difference in your resistance, so the resistance with the mean parameters and the resistance of your structure with the characteristic parameters, you are able to determine a material factor, or a factor which will be applied on your resistance. That will then be compared with the applied loading. And then you have the partial factor method. In that method, you just perform analysis, only not with the mean parameters, but you will perform analysis with design values. So it means you will use a lower concrete strength and a lower tensile strength, for example. There are some discussions about these safety formats. And that is because when we are performing a nonlinear analysis using finite elements method, we would like to model the realistic behavior. And the most realistic behavior is found when you will be using the mean values. So for example, for the ECOV method, I will perform 2 analyses, one with the mean values for the parameters and one with the characteristic values of the parameters. It is possible that in the first analysis, my beam fails in bending, for example. And then I perform the second analysis with the characteristic material parameters, and my beam will fail in shear. Yes, this is something which is not really thought of what to do when that happens, because it can be that then the shear resistance may be even higher than the first calculated bending capacity. Yes, so it is quite important. Yeah, so the thing is, what we want to do is to describe the behavior as realistic as possible, but still take into account some sort of material variation, and also the dependency on the material variation in your structure. So actually, that's only done with the probabilistic method. Only the probabilistic method is very, it takes a lot of time and a lot of work to perform a number of analyses. So that's not very practical. In the bottom, I wrote it down what we are actually looking for. It says here the sensitivity of material properties on the total resistance and the failure mechanism. So that means that you're not really allowed to switch your mechanism when you change your material properties, should be taken into account in a safety format for nonlinear analysis. So basically, you would like to do a nonlinear analysis using the mean values, but still then you would like to know whether it is very sensitive in changing of failure mechanism, for example, or whether it's sensitive to the tensile strength. Those things are not very nicely incorporated in it, in these methods which are here now, with the exception of the probabilistic methods. So to check sensitivity, this is where actually, Diana has introduced this new feature. That is also the idea to check whether your model or your structure is sensitive to a change in failure mechanism, for example, or whether it's sensitive to a change in a certain material parameter. So what we do, I will explain it later in the live demo. We will actually do a sort of investigation on the sensitivity of the, in this case, the tensile strength. And we use the new feature, strength reduction for total strength crack models for this. To do that, we first have to apply a certain load, let's call it the ULS load, in a nonlinear analysis. And subsequently, then a strength reduction analysis can be applied. That says here also, that's basically the procedure. Two analysis in a row. They're both nonlinear analysis. In the live demo, I will will treat two beams, but only one I will be modeling in this webinar. So it says one beam which has an expected bending failure, and one beam which has an expected shear failure. And the beam which is expected to fail in shear, I will model that one in the webinar and also discuss that one, or I will discuss both. But so this is the beam with the bending failure. It's just a simple 4-point bending test, and the beam which will be modeled in the live demo. I will start with that now. And then also during the live demo, I will have some background information regarding the strength reduction method. I already opened a new project. So let me get first to the project settings. We're only using the structural module. It will be a two-dimensional model. I will be using quadratic elements. First thing, since we're going to do analysis with concrete, in general, it's handier to use Newton, millimeters, and tons. But that's also personal preferences or preference. We start by adding the sheet for the beam. So we name it beam, and it has a length of 5,000 millimeters and 500 millimeters high. We create. Next step is creating the loading plates and the support plates, also by adding a polygon sheet. So first one, we name this one loading plate. Okay, you can see here that it is the preview. You can see that we're leaving a point in the middle. This is the point where we will attach the loading later. So we create this one. Start by creating the next loading plate. Second. And here we see the second loading plates. Create. Next step, so we have the loading plates. Next step is the support plates. We can generate it in a similar way. So next step is creating the support plate too. Instead of just creating, of course, all the points, we can also make an array copy. We have to use the distance, and then we can see, yep. So this is then our beam with the supports and the two loading plates. Next step is the addition of all the reinforcement lines. Starting with the long bars at the bottom. So they are over the full length. Also in this case, I will just array copy it. Select it, and then because there will be two bars just slightly above each other. Also, we're making the long bars at the top of the beam. And the top bar, we can also array copy this one. Apply. So above the bending points, we're also going to apply some extra reinforcements. So here are the two loads. We will be expecting the highest bending here and here, or at least the highest tension there and there, due to bending. So we're going to add their extra reinforcement. And we name those short bar. Short bar bottom. So we will be positioned here. And then we will array copy it also upwards. create. And then we will create 2 short bars also over here. And you can see it. Okay, so now all the geometry part is finished. We can start by assigning the materials and the geometries. We'll be starting with the beam. We'll use plane stress elements and start by adding a material. The materials are all concrete. And we'll be using the concrete and masonry, and then the total strain-based crack models. And here you can see the option strength reduction. So we want to include that in our model. Starts with the Young's modulus, where we'll be using more or less the mean values because we want to model a realistic behavior in this case. We will be using rotating Hoordijk as for the tensile strength. And the Torveld for the compression. I fast go through the total strain crack options. Because this one is more about the strength reduction type. Here are the options which you can choose for the strength reduction. You can choose to either reduce the tensile strength in the analysis, the compressive strength, or both. In this case, we just would like to investigate what will do the tensile strength on our resistance and the stability of our concrete structure. So we just choose tensile strength. We still have to add a thickness for the beam. Okay. We see updates. We do the same for the support plates and the loading plates. Okay. Select. We also choose regular plane stress elements. I will be using a linear elastic material for these plates. Just name it steel. And the geometry, you can use the same one as for the beam, since we will just use the same thickness. Next up is all the reinforcement. All the reinforcements will have the same properties. It will just be modeled as embedded reinforcement. Info. Also, to keep it a bit more simple, we're not expecting any yielding, so we're just going to model the reinforcement linear elastic. And then we only have to input the Young's modulus. For the reinfo, for the geometry, we'll be using 400, which is more or less similar to 2 bars of, with a diameter of 16 millimeters. And we will be applying this as well. So we have created the geometry shapes. We have assigned it. Next step is to assign the supports. And we would like to assign it to this point. This point will be a hinge, so that means we're only going to fix the translations T1 and T2, which correspond with the X direction and the Y direction. Create. And DC2, which will be only supported in the second translational direction, which will be the Y direction. Next step is to add the forces. That will be the point loads. Yeah, just name it load 1. And this will also be a vertex, so a point load and a force. In this case, we will be using a unit load. So that means we'll give in now 1 kilonewton for this one, and later 2 kilonewtons for the other one. But in our load factor later in the analysis, we will be increasing this, the load factors over 1. So that means that this is just the unit load and will be increased later. Yeah. So now we have our supports and our loadings. So the last stop for the finite element model is to set the mesh size. Mesh properties. The shapes, you want to set an element size. Select. In this case, we will be using 50 millimeters. Yeah, it's normally maybe I would choose a little bit smaller, but in this case, since we're doing the webinar, just click. We also would like to see some results from the analysis, and then it just calculates a lot faster. So if we generate the mesh, this will be our finite element model. So with the loads and with the supports. Next step is then to set up the analysis. So we're just going to add an analysis. As I said before, we have to perform first a just regular structural nonlinear analysis. And then after that analysis, we can perform the strength reduction. So in this case, you would like to choose a ULS load, and that will then be applied. So we'll be giving a stop load, and we'll set the load up to a certain factor. I will get to that later. First, what we choose for the nonlinear effects is only physical nonlinear. Since you want to take into account the cracking and crushing of the concrete. As you may have noticed, we have only created one load. In this example, we skipped the dead weight. Usually you always start with first the dead weight and then the other loads. But it was just to keep it as simple as possible. We will be starting with a few larger steps, because the first part is expected to behave linear elastic and then increase the step size. Since you're performing a force-driven analysis, we will be using arc length for two reasons. One reason is that cracking is expected, and cracking could initiate that our load factor will drop down a little bit, so it will decrease. We cannot capture that if we do not use an arc length or placement control. The other reason is that if you use arc length, when the nonlinear effects increase, you also see that your step size is automatically decreased. Yeah, that's inherent using the outline method, but it's also a benefit. Yeah, we would like to control a little bit the arc length, and since we know that the deformations will be in y direction, we can choose the y direction. And in this case, we are choosing 2 nodes. Select 2 nodes. We know for sure that those 2 nodes will be moving in the y direction downwards. So it's easy to choose those nodes to control the arc length. Yeah. As I said before, next step, I'll first set the iterations, by the way. So the iteration screen would just be using Newton-Raphson with a line search to improve the convergence for cracking. We will use the convergence norm energy, which is a bit more strict, but we will set it to continue if it doesn't find convergence, to just go through the full analysis. And also for concrete, this is in some cases is allowed, because we're not, especially for engineers, it is allowed to be used. Because we are not a research institute who want to know the exact solution. If we can find the solution within 5% of the exact actual solution, it's still good enough. And you see, if you put it on content, if we do not deflect from the convergence norm too much, so not if we find a very strange path, then we say it's not good anymore. But if we keep fairly close to our convergence tolerance, the results in most cases are still very okay. As I said before, we were using a unit load of thousands. So to set it to an actual load, we're going to use a stop criteria. And in the stop criteria, I can set, okay, I want it up to 68, for example. And since we're using the arc length, it will decrease the step size. So it also knows we do not know how many steps we will be needing from the load steps. Since I fill in here 5 and 1, but through the analysis, these step sizes will be decreased. And I want to end exactly at 68. So therefore, I will be using a total load of 68. Another option which I use is to switch on the R-flag method in the last step, because what happens if I use the arc length, when we perform the analysis, when it gets closer to 68, it tries to end exactly at 68, and in combination with the arc length, in some cases that could lead to very small steps. So then I say just switch off arc length in the last step, and then it uses a normal step in the last step to end at 68. We'll be adding some outputs. I will be only adding in this case the least, which is necessary. Those are the displacements and the crack width. Because every option you choose as your output is also, it takes extra time in the analysis. And for the reinforcement output, I make a separate block, an output block, where I say do not use the elements, only results for all the reinforcement. This is again to also save, to speed up the analysis. So then we do not have to determine the output for the stress for the concrete elements. So this is the setting for the nonlinear analysis. And we can now also add the Where is it? Strength reduction. I will just set the settings for the strength reduction rather fast, and then I will start the analysis, and then I will explain it later furthermore, and also explain a little bit what I did and how it works. One moment, almost ready. I will be adding a stop criteria as well for the strength reduction. And in this case, it will be a temperature or a result-based stop criterion, because actually I only wanted to stop when the failure mechanism is there. So when the analysis becomes unstable, but I still would like to see the unstable results. Normally, if you use a strength reduction analysis, you will see the results up to the unstable part, and you do not get to see the results of the unstable part. Also the same output here, so principle. Yeah, and then I can also add the tensile strength output, this one, because we will be reducing the tensile strength in this analysis. And then we can see how it develops. Also the same for the reinforcement. Okay, I think that's it. Okay, then we can start the analysis. And then I can explain a little bit more about the strength reduction. So now the analysis will calculate everything, and then I will get back to that later. Here is a flow chart of how it usually works and what it is also used for. So the strength reduction is used to determine the factor of safety. And in general, it is used for geotech applications, so for geotechnical analysis. You can also see here in this example, there is also scaling the cohesion and the friction angle. So it already shows that it's more for, that is also, for at least originally, it's used for geotech applications. But now it can also be used for concrete, only then the tensile strength. So how does it work? We start with F as 0, so that's the initial factor of safety. In our case, that is 1. Actually, I think in any cases that is 1. So that means that is the start point of your analysis. And what we're then going to do is increase the factor of safety with increments. So you saw it in Indiana. You had the option to choose the increment size. I can quickly show it again. In your factor of safety settings, you have the option of the initial factor, which is it's 1, which should be 1, and you have the factor of safety of increment. So this increment is used. Any iteration, the safety factor will be increased by 0.01. That is what is stated here. And then, so in this case, the cohesion will be divided by the factor of safety. But in our case, the tensile strength will be divided by the factor of safety. So the tensile strength will be lowered. If internally that is lowered, and then Diana is going to try to find convergence between the new internal forces and the external forces. Because we now lowered our tensile strength, in general, the stresses are a bit lower. So there will be an out of balance force between the inner and external forces. And we will be using a start step to remove that out of balance force. That's also what you see here in the execute step. These are actually the step sizes which you can choose for your start step. And this should be always 1. So in this case, I used 2 steps of half, but in most cases, it's also good enough to just use 1 step of 1. So we try to find convergence. If there is convergence, go to the next increment and do the whole procedure again. Up to the maximum value initially. So as you can see here, there's also a maximum factor of safety. That's to prevent that it doesn't continue forever. Or is it? Yeah. But if we do not find convergence, that's also an option. Then the factor of safety, or at least the increment of the factor of safety, will be divided by 2. And that will then be added to the original factor of safety, and the analysis will be performed again. And then if there's not convergence found again, then again that increment will be divided by 2 another time, and it will be a retry. Until it is smaller than the tolerance, because then it's also stopped. This is usually how it works in general. So that means you saw that also for my convergence options, I used continue even when there's no convergence. Then this flowchart doesn't work anymore. So you have to say terminate, and then the factor of safety will be divided by 2 if there's no convergence. If you use contin, that is allowed, of course. You can just use contin. It is handy to use a stop criteria, because then it uses stop criteria whether to determine it will go this way or it will go this way. So instead of converge, it says, is it still within the crack? Is it still large? Are the cracks still smaller than 1 millimeter? That's now the question actually which stands here. You can also not use the stop criteria. But if you do not use the stop criteria, it will just continue up until the maximum factor of safety. That's also okay. But because I wanted to see if we can also see a shear failure, and if a shear failure occurs, usually the cracks are a bit bigger. So in that case, I set it to 1 millimeter. In this case, this one is still calculating. So I think it's better if we first check out what happens for the one with the bending problem. I already did the analysis for this one. So also here we performed the structural nonlinear analysis, and we performed the the strength reduction. In this analysis, we set the ULS load a little bit lower, of course, than the ultimate load. So if we would check for the results of the nonlinear, you would see something like this for the deflection. So this is something like this. Then we see here first the initial brands, then we see the cracking, and here we see the stiffness of only the reinforcement, and then this probably will continue up to the plateau where the reinforcement will be yielding. So this will lead to the crack pattern, which looks something like this, which is a typical, typical crack pattern for a bending problem. So what we'll be doing now is to reduce the tensile strength which is used at the moment. So that's the 3.8, and we will reduce it and see what will happen to a beam which is failing and bending. This is then the reinforcement stresses which fit with it up to 360 or something. So first step is where the safety factor is still 1. So we can see that the results are still the same as how the structural nonlinear ended. So this is the same behavior or crack pattern. Also the crack size is the same. So it was also here 0.7. Also here it is 0.7. And you can see this is the tensile strength is 0.8. So I can show you how it goes, how it develops through the analysis. Let me first show you what I did for this one. I didn't use a stop criteria for the strength reduction, and I only set the maximum factor of safety to 5 because I was expecting already that it not too much would be happening if the strength would go down for a bending problem. So the increments are 0.2 and then up to a maximum factor of 5. So that means that the tensile strength will be reduced to 3.8 divided by 5. And you can see that here also in the table. It goes from 3.8 up to 0.76 or something. Yeah, 76. So that is that's 3.8 divided by 5. If we now look at what is happening in the beam, we can actually see that not too much is happening. So the maximum crack width is 0.7. And it more or less, it stays at that value. The only thing what we see here is that more cracks are added. That's because of the cracks of the zones where there's no crack. And now the tensile strength is reduced, and now it will be cracked. But that's the only difference. Also, when we look at the reinforcement, we can see that the reinforcement stresses are more or less kept the same or even a little bit reduced, even though the force is kept constant. And actually this already makes sense, at least for me, because in the case where we were looking at now is that the concrete is already cracked. So most of the tension strength is already carried by the reinforcement, and not really the influence of the concrete which is still there between the reinforcement is not so high. So you can see that if you have a bending problem and you will reduce the tensile strength, this won't really influence your tensile capacity. So you can say for this failure type, my tensile strength is not really sensitive for the tensile strength. Okay, here we can see that it is now ready, the shear beam. Also, first look at the results for the structural nonlinear up to load factor 68. And we can see that only some bending cracks have occurred at the moment. And the idea is now, if I would lower my tensile strength, I would like to see actually the shear cracks. We can see that also happens. Here we can see if we go to the strength reduction, this is the first step. It's still similar to the final step of the structural nonlinear. If we now continue through the steps, as you can see, I used fairly small steps to reduce the tensile strength, but that's because it's quite sensitive to it. So you can see that some cracks are occurring, and then all of a sudden you can see that here already some shear cracks are trying to occur, and then it is they're occurring already at a safety factor of 1.13. So that means, in this case, this beam is quite sensitive to shear failure, of course, but also to the tensile strength. Which, of course, it makes, of course, sense because when you look at the room, you're expecting shear failure. But also the fact that shear failure is also quite brittle behavior. So that means we see now actually quite an unstable failure mechanism. And when you look at sort of safety formats, when we were looking at the beam in bending, it makes sense not to use a sort of material reduction factor for something like that, because even though you decrease the tensile strength, it doesn't really influence the results in the end too much. For the shear failure, you can see that it's very important. So for this kind of beam, we should see how we deal with this kind of problems. And with the strength reduction option, you can at least show that it is sensitive to a change in material parameters. That's actually the most important things we would like to show with it. And so, that's indeed what I wanted to end with. It is an option which should show you whether your structure is unstable or relatively stable still after applying the ULS load. So thank you for listening all.